In this video, I will describe our model called RapidNet, which we use for accurate packet identification, and subsequently, this model is integrated with Autodoc Vina, but you can integrate it with any other tool. And eventually, this is used for binding site agnostic docking. So when you have no idea where the ligand should be docked, but instead uh, like the, first you need to identify the pocket, and additionally our model is able to identify not just the pocket where the ligand is likely to reside, but also remote protein sites that indirectly affect ligand binding, which provides deeper understanding of protein ligand interactions. So like for example in these two ligands, this work corresponds to this our paper, and you can take a look at it here. This is the overview of our model. First of all, our model uses soft labels to when predicting pockets, so it's not a binary mask. And also we use L2 soft dice loss function, unlike like regular dice loss function, which is used in most pocket predictors. Why? Um, yes, so additionally we use attention blocks, and what is also interesting is that we found that removing redundant residual connections actually improves the model performance. So essentially, the pockets that we are predicting, they serve as initial approximations for Autodoc Vina search grids, and this provides, as you can read in our paper, this provides great improvement in docking efficiency and accuracy. So I would like to illustrate this by this protein 8F4G. So essentially the main, so docking the ligand is like digging for gold, roughly speaking. When you are digging for gold, the main factor influencing the success of gold digging is to know or like to guess with high accuracy where you should be digging for gold. And this is similar for ligands. So, for example, there is this protein 8F4G, 4J. So essentially, I will show how our model handles this specific protein, and you can. So to do that, first you need to go to Zenodo, and here is a notebook for achievers for performing this task. So what are you doing? First, you are downloading this notebook. It's going to take a while. Let's see. Download. First, you wait. You wait. And after the notebook is downloaded, you can upload it to Colab. So essentially you go here, you press upload notebook. So let's wait a little. Yeah, I will pause the video first till it downloads. It's a large notebook. Okay, so after this notebook is downloaded, you go to upload notebook, you press browse, and then you upload this notebook. It's going to take a while it uploads, so I'll press pause for a second till it uploads. Okay. Oh no, it's uploaded already. Okay, that's good. So let's wait. Okay. So here is a notebook for performing this docking. So let's close this. And essentially, what is it doing? So first of all, you need to first of all you need to set up your Colab environment. So you press this button. This will install Conda Collab, and after installation, it will crash the session. So it will be you will have to restart the session. So when you see that your session crashed for unknown reason, this is normal because essentially it just means that your session is restarted. So let's wait. Session crashed, and now you press this button again. So you just press it again. And after that, you initialize. Okay. After that, you initialize your model for packet prediction, and essentially, there are some user inputs. This model operates as follows. So first, each voxel 2 by 2 by 2 and so all your protein is split into such cubes of 2 by 2 by 2 angstroms, and essentially you assign some specific voxel to be belonging to your pocket if the model is thinks that probability of belonging to the pocket is greater than 50%. So by default, this is like 50%. You should, so you can say, 50%, it's not much, but the issue is when you train this model, in fact, the number of interacting voxels is much smaller than the number of non-interacting voxels, and that's why, like during the training of the model, we actually perform in class reweighting. So like 50% by default, you may say, oh, it's not much, but in real life, it's already sufficient. Like just imagine, like someone would tell you that at some location with 50%, you can dig out the gold with like $1 billion worth $1 billion. So you would try that, right? So also our model works both with so essentially our model actually consists of ensemble of 5 models, so 5 replicas of RapidNet model. And we output the pocket predictions of 2 types. First pocket prediction is like consistent of voxels that are voted by at least 3 out of 5 models, and this is we call them majority voted pockets, or pockets or like pockets that comprise of voxels consisting of like which were predicted by at least 1 model out of 5 models. So sometimes, so it depends. Sometimes model thinks that this majority voted is like usually those that are majority voted, they actually are more reliable predictions, but sometimes actually minority is actually correct, so you should take into account both. And now we are pressing this button, so we are initializing this model. So we are installing dependencies which we need to process our proteins, so Py3DMO, BioPython, RDKit, and after that, our model is. Then we initialize the model itself, and we are loading the model weights. We saved the trained model weights to Zenodo, so it's uploading automatically. Let's wait a little. Just grab some coffee. Right, so now your dependencies are installed, and now you are launching this model for predicting pockets. So first we download weights from Zenodo. Yeah, it will take a little. It will take a while. Maybe I will pause the video here. Okay, so now the model is downloaded, so you can see that we downloaded the model weights, and after that those weights were loaded into the model itself. So now our model is ready for pocket prediction. So for this example, I would like to consider this protein 8F4J, which AlphaFold 3 cannot handle as a whole. So essentially, the same notebook can be used for any protein in those datasets, in dataset Postbusters or Aztecs. However, I would like to consider this specific protein for illustration because basically this is the screenshot. You can just go here. This is accurate structure prediction of biomolecular interactions with AlphaFold 3. And if you just type 8F for J, you can see, so basically this protein was too large to inference the entire system. So AlphaFold essentially was unable to dock the ligand to this protein as a whole, but instead they just cut out the part of the protein where the ligands were binding. However, this is unfair. So this is effectively this is cheating because in real life you don't know a priori where the ligand is going to bind. And so essentially that's not good, right? So and how uh, however, as I will show, our model is capable of processing this protein as a whole. And essentially, just by accurately identifying the likely location of ligand binding. So for this protein, first of all, you can go to Zenodo. Zenodo. So you go to Zenodo, and here is this protein, and let's first you download this protein, and you can actually just Google 8F 4J protein. So essentially this is this protein. It's essentially a really large protein, right? Something huge. uh, and first you unzip this. So first you unzip it, right? Um, then you go, okay, so then what do? You, wait a second, where's Google, wait, then you go to Colab, and so first you can, so first this is like you can enter the name of the job you are going to submit. So in this case it's just this protein, but you can type anything you like. This one predicts. This one shows what type of pockets would you like to for the model to predict. So both minimally reported or majority voted. I've chosen both, but you can customize it as you like. Then here you can input the threshold. So essentially, when you are assigning the search grid, you are putting your essentially you are putting some box. You will see it later, and essentially, okay. Essentially, what this is doing is just saying how far from the pocket you are going to look. So this is 2 angstroms. So let's press. So let's upload our protein. So this is our protein, and you upload it here. And as I said, this is a large protein. This is it is quite heavy. So it would take some time to process. Maybe I would pause the video at this point till this protein is processed. However, for smaller proteins, it works way faster than for this one. But this is because this is just a huge beast. It's really a large protein. Okay, so just to give you an impression how fast is it working, so essentially 4 minutes it took to just upload the protein, and this is prediction by one of the models from Ensemble. So actually, Pocket prediction is taken quite fast in comparison to like preparation for docking itself and docking. So even though it's really important to accurately assign pockets, it is it takes not so much time, but this is a critical step. So you can let's wait just to see how much time is it taken to predict the pocket, only the pocket. And after that, I will pause the video again because it's going to take a while for the protein to prepare the protein for docking. Yeah, okay. Basically, after uploading, it takes 2 minutes to predict the pocket for this protein. But again, like for smaller proteins, it takes way faster, right? So I will pause the video now. Okay, so basically, it took like how many, like 5 more minutes to predict all the pockets. So basically, because we have 5 models in Ensemble, that's why you can see here 5 lines, right? So both majority voted and minimally reported pockets were generated successfully. So there are several bugs in this clustering or like segmenting procedure. So basically, the model predicts density distribution, and based on that then density distribution and based on that density distribution of those pockets, you segment them into pockets. Some of them are just, yeah, but the problem is that some of them are just junk or some of them are empty. So there is an automatic procedure to erase those junk pockets. And here you can see a list of final list of pockets that were saved. So basically, all invalid pockets were filtered out. And now what this program is doing, so now we are, so after we found the pockets, we are preparing the protein for docking. And for that, we basically generated, so this is the folder corresponding to your protein. So in this case, this is 8F4J. For each pocket and for each search grid, we have a separate subfolders. So they will be filled in after we perform the actual docking. Basically, we generated a config file, we generated the results directory. Now, what do we do? We use reduce to assign explicit hydrogens for the protein, which is a crucial part for docking. And okay, at least in this case, we used the older version of reduce, but keep in mind, so basically this one, but keep in mind that currently there is reduce 2, as there is a newer version of reduce, and I guess in the next update of our model we will include this newer version of reduce 2. Reduce 2. And now you can see that it's performing optimization of hydrogens. And now there is after performing after protonation of the protein was reduced, you have to remove bad atoms. So basically, atoms that rarely occur in proteins and which can spoil the docking procedure. So first we remove those atoms, and now it will also take several minutes to actually prepare the protein for docking. So essentially to generate a PDBQT file. So I will put a pause here because it can really be like several minutes, maybe like 5 minutes or maybe 10 minutes. So essentially it's so as I said, like uploading the protein and basically predicting pockets is way faster than performing all the steps needed for actual docking. So I will be back. Okay, so basically, finally, the protein is prepared for docking. So actually, you can see that it took approximately 3 minutes just to upload this protein because it's heavy. It took approximately 7 minutes to predict pockets, and it took around 16 and a half minutes to actually prepare a protein for docking. So you can see that pocket prediction actually is relatively fast. So docking itself, even though accurate pocket prediction plays a crucial role in accuracy of the docking. Um, yeah, okay, so now you need to upload your starting confirmation of your ligand for the docking, and this is this one, 8F4J ligand starting confirmation. So you press this button, and now your ligand is prepared for docking. So ligand prepared and saved. Now let's take a look at our protein and predicted pockets. So in this case, this is like 8F4J and majority voted pockets. Let's wait till it uploads. Yep, here it is. Mhm. So here is the protein. Here is the protein, and here are the pockets, the predicted pockets. So you can see this one, this one, this one, this one. So basically, these are majority voted pockets. Now you can take a look at the same protein, but with minority reported pockets. So essentially, pockets comprising of those voxels that are predicted by at least one model from ensemble. So you can see it shows more possibilities. You can see here, 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 here. And yeah, but we are for simplicity we are just performing docking only with majority voted pockets, and as you will see, this is actually sufficient to achieve accurate results. So now what I'm going to show you is this protein and the search grid. So actually, we can take a look at this. So you can see that this is your protein. This is this huge protein, and this box is actually the search grid where we are looking. So it's one of the search grids where we are looking for the ligand docking. So essentially, what is important to note is that uh, you know, like for example, AlphaFold, they are saying that this protein is too large to be processed, so that's why they just cut out this like lots of like basically a large part of the protein. However, uh, what you can see from here is that essentially you don't really have to process the whole protein, because what you really need is an accurate search grid. So essentially, you don't have to look for docking throughout the whole protein. So essentially, this one you will see later that essentially this is a search grid which is actually brings us success. And you can see the search grid is actually it gives you the center of the search grid where it's centered, and this gives you the box size like 20 angstroms by 30 angstroms by 52 angstroms. So this is because our essentially our cells, they are all uh, they all proportional to 2 angstroms, because this is 2 by 2 by 2 boxes, right? Now we go here, and now we start the actual docking with those generated grids. And this is going to take a while, so I will have to pause the video here. But essentially, this takes as input this grid centers, grid sizes, and takes as input this proteins that we prepared and ligand. So here I'm going to pause because this is going to take quite a while. Okay, hello, I'm back. So basically, in 2 hours, okay, yeah, I'm back. So in 2 hours, the docking was performed for all available packets. So essentially, if you go here, you can see, you should be able to see them. Okay, come on. So yeah, so you should see the docking reports as well as ensemble of predicted poses. So and that's what you can see for each predicted pocket. For each predicted pocket. Okay, now you do this. So in at least in this paper, what we did, we've chosen the most energetically favorable pose based on VINA scoring. So essentially based on VINA scoring function. You should keep in mind that essentially reweighting VINA predicted poses can boost accuracy. So not necessarily you have to do that in practice because, like for example, these in solid lines are results for those poses that are those cases of proteins and ligands which are correct, like top one is correct. But in these dashed lines, you can see that these are the parts which are uh, correct but not top one. So essentially, what I'm saying, if you, for example, take a look at this, yeah. So, for example, this. So there are other, like in our paper, you can take a look. I've collected a list of other proteins that, for example, top one Vina pose fails the test. However, subleading Vina pose, which is not top one, actually passes the test. And there are, in fact, lots and lots of them, such poses, like how many? A lot, right? So basically, you can boost the accuracy if you have a more reliable way of reweighting your poses. You can drastically boost your accuracy from kind of 56% to 92%. Um, yeah, and let's see. So there are several examples of this. I've provided several examples of such cases when subleading pose is passing the test, but top one doesn't. Like for example, this one. So top one is this one, but this is subleading, and it passes all the tests. And like for example, top one is this one, subleading one should be less favorable, but it passes the test. And in fact, if you just take a look, in fact, Vina is actually good at predicting good ensembles of poses. Essentially, if you take into account those poses that can be recovered by reweighting, just by assigning different weights, like for example, saying that second pose is in fact top one, for example, then in fact it outperforms AlphaFold, especially in blind docking settings when you don't know where you should be docking the ligand. And this indicates a great potential for our future work because essentially if we complement this framework with a better reweighting tool, we can outperform AlphaFold, but using much less computational resources. But in any case, in this case, in the case for this protein, it is still working even with VINA scoring function. So essentially, it is actually the solid line. So let's do this. So what we are doing, we are checking all the pockets, and among them we are choosing the most energetically favorable poles, but based on Vina scoring. So essentially after that we are getting like number of scores, and we finding the poles with the most negative score, and we are saving this poles into as our predicted one. And now at this point you can upload the list of true poses. So you need to choose this file. Make sure that when you do this, you choose not ligand, but ligand Z. You see the difference? Ligand, ligand Z. Because this one, so this is actually used in Postbusters only for centering the search box when you don't have a pocket predictor, right? So you need to choose this one. Okay, so you've chosen, so you've got all this. Okay, and now, according to the rules of this Postbusters game, if the predicted pose passes the test with respect to at least one of the ground truth poses, it is considered a win. So, if at least one, because in some proteins there might be several places where a ligand can bind. So, according to this game, if you find at least one such place, then you win. And essentially, all this procedure, it has an element of randomness. And sometimes, actually, it gives you slightly better, slightly worse results. So here I'm going so here is an example of absolutely perfect run. So, like for example, you can see that there are four true binding poses, and like this one is far from that, this one is far from that, but for this one, we actually passing RMSD test, and additionally we are passing all Postbusters tests. So you can see, so we are passing all Postbusters tests, and as a result, we have that our pose passes both RMSD test and Postbuster test. So in this run, everything was successful. So I ran this code several times, and I saw that sometimes, so basically all the time you have RMSD less than 2 angstroms, but sometimes you may have one or two Postbusters tests failed. So basically, if this time something fails, you just you can do first. You can rerun this and to get a absolutely perfect result, or you can perform energy minimization as was done in Postbusters test, when basically when you have correct RMSD, but and some of those Postbusters tests you can fix, and those Postbusters tests are actually things like chemical validity and all that stuff. So now let's do this time. So let's see what happens. Okay, so you are installing this. Okay, and now you can see this, right? So first pose, it's not our candidate. Second, no, it's not ours. And yeah, but this one actually we are matching this guy, right? So 1.3, and because sometimes it's jumping around this number a little bit because there is an element of randomness in docking. So in this case I had 1.29. In this case, I'm having 1.32 roughly. And now we need to wait a little till all Postbusters tests are checked for the chemical validity. And again, as I said, sometimes you can, so you already see that RMSD is correct. Sometimes some of those RMSD, sometimes some of those Postbusters tests, they fail. So, you know, if you want to completely reproduce this, you can try to run it several times or perform energy minimization. I will put a pause on this video because it would take some time, maybe several minutes, for this protein to process, because it's a large protein. Woo. Okay, congratulations, congratulations. So, in this case, you can see that 1.3, right? And all tests passed. So essentially, all tests passed, but um, okay, so all tests are passed. So this is absolutely perfect. So I'm just telling you that sometimes, just because of randomness in this docking process, some of those tests may fail. Yeah, and in fact, in our paper, we said that in our paper, in fact, we said that one of the tests was actually failed. So RMSD was 1.3, but one of the tests was failed. In this case, actually, so in this case, it's actually absolutely perfect, but, congratulations, right? Okay, now let's take a look at where, with respect to the pockets, we have these docked ligands. So basically, let's show this protein with majority voted pockets and true binding poses. So if you take a look at this, these are the pockets, right? So these are the poses. So some of the poses are completely covered by pockets, but some are not by majority voted pockets. And now let's take a look at just pockets, predicted poses, and true poses. So you can see that, so this is the same image but without protein, so just pockets. So you can see that this one is kind of one of experimentally determined poses. This pocket doesn't show this, but if we find at least one true, we win. So actually, if you take a look at this, so this is a clear win because you can see that red one is the true ligand binding pose. Then let's see, right? So red one is true ligand binding pose. Green is see, yeah, green is predicted binding pose, and this is the majority voted pocket, which is saying that like where the pocket predictor thinks that ligand is likely to be. So you can see that they actually overlap, and this is nice, right? So you see this nice overlap. So right, uh, actually sometimes. Our pocket predictor doesn't show all possible poses, so it's also not perfect. But sometimes it does. Like for example, you can see for this protein. So this is the protein 2ZJV. And in this protein, you can see that actually there are 5 true ligand binding poses, like this. And in this case, you can actually see that our pocket predictor has majority voted. Like it is predicted all 5 pockets and confidently. And actually, you can take a look in our paper that for this protein, it's also showing the bridge towards the F loop, which is known to have like induced fit movements and which are essential for ligand recognition, right? So essentially, these are the residues that have an indirect impact on the ligand binding, and actually, that's what we are identifying here. Like you can see this bridge, you see this bridge, right? Okay, now let's compare our predictions to PureZNet version 2. So this is another recent pocket predictor. So to do that, to simplify your life, I've just downloaded all the files to Zenodo. And here are these files. And then if you just upload this, you can see that yeah, so you can see that our pocket predictor is working much better because basically like these are kind of scattered or all over the place, and true binding poses they are actually not shown. But in our case, we have a clear separation and a clear segment, basically segmentation. Basically, just put the box around this, and you will get this duct without any prior knowledge of the binding and of the binding site. And one more thing I wanted to show is that actually, what about minority reported pockets? So you can ask, okay, so majority, but what if majority voted pockets are wrong? So maybe minority reported pockets are actually correct. So they actually partially correct. So here you can see that two poses are uh, completely covered by pockets. You can see that when you consider minority reported pockets as well, you can see that third pose is also partially covered. So this one you can see, right? So actually, if you would put some sufficiently large search grid, like 5 angstroms or 10 angstroms around this, you would find this pose. But this are just this are just for comparison. But and just to clarify, Postbusters game, we already won this Postbusters game because basically according to this game you win if you find at least one true binding pose, and we already found it. So actually we already found true binding pose. In our case, this is pose number 3. You see this, right? Pose number 3 pass RMSD less than 2 angstroms. Okay, now let's make a just a quick comparison. So uh, if you would do predictions with fpocket, so if you would install fpocket, so yeah, so essentially if you would predict using fpocket, you will see that basically like it would be scattered all over the place. So let me pause the video for some time till fpocket is installed, and uh, till fpocket is installed, and after that I will run this, but just to save time I will pause this video. Okay, so essentially we just predicted the alpha spheres by fpocket, so you can see that they are basically scattered all over the place. And actually, if you take a look at, if you compare this to even to minority reported pockets, it's a much larger search space than it would be for minority reported pockets. Like minority reported pockets are essentially showing just this part of the protein as being likely to bind, but fpocket is scattered. Fpocket alpha spheres are scattered all over the place. And just to provide the reference, so um, in AlphaFold essentially uses pocket information, and this pocket information was provided by fpocket. So essentially that's what you saw here, and as a result, so I think this is a root cause for this. So basically for the fact that AlphaFold 3 cannot process this protein as a whole. So I mean, this part, right? Oh, yeah, anyway. Where is that? Mm, this part, right? So this is why AlphaFold cannot process this protein as a whole. Okay, thank you for your attention. I hope this was useful. So If you have any questions, concerns, bug reports, please write on one of these two emails. And if you find this neural network useful, please cite us as well in this paper. So thank you for your attention and have a great day.